Welcome to this chapter on data foundations for AI in construction. Modern construction projects generate a tremendous amount of information every day. Design files, estimates, schedules, RFIs, submittals, inspection records, daily reports, field photos, equipment data, and commissioning documents all become part of the project record. But in many projects, this information is not used as effectively as it could be. Project teams often spend valuable time searching for information that already exists somewhere in the system. Sometimes the information is stored in different platforms, different file formats, or different versions. As a result, decisions become slower, coordination becomes harder, and the risk of rework increases. This is especially important as construction moves toward artificial intelligence. AI tools do not create reliable knowledge by themselves. They depend on data that has been collected, organized, validated, and connected. The key idea on this slide is simple. Raw project records must become clean, integrated data before they can support useful AI insights. When the data is accurate and accessible, AI can help managers identify early warning signs, predict potential delays, improve decision-making, and reduce cost impacts. For construction managers, data should not be viewed as simple paperwork. A daily report, an RFI response, a schedule update, or a field photograph can become a valuable management resource, but only if it can be found, trusted, compared, and reused. So, in this chapter, we begin with the foundation. Before AI can improve estimating, scheduling, progress tracking, safety, quality, or field communication, the project data behind those tools must be reliable. Construction data comes from many different sources, and each source supports a different type of management decision. First, we have BIM and design data. BIM models contain geometry, materials, spatial relationships, system information, and project intent. This data can support clash detection, quantity takeoff, constructability reviews, and model-based comparisons between planned and installed work. Second, we have project management and ERP systems. Platforms such as Procore, Primavera, P6, Oracle, Microsoft Project, and accounting systems store important project information such as schedules, cost codes, budgets, procurement records, payroll data, and approval workflows. When this information is entered consistently, AI can compare planned and actual performance, identify cost trends, and support schedule or budget forecasting. Third, construction projects generate a large amount of field documentation and unstructured text. RFIs, submittals, contracts, change orders, daily logs, safety reports, and meeting minutes contain important project knowledge. With natural language processing, AI can help read, organize, summarize, and retrieve information from these documents. It can also help identify scope gaps, compliance issues, and early warning signs of delay or dispute. Finally, we have reality capture and IoT data. Drones, 360-degree cameras, laser scanners, fixed cameras, equipment sensors, environmental sensors, and wearable devices can all provide visual or real-time information from the job site. AI-based computer vision can compare field conditions with BIM models, track installed work, and identify visible safety or quality concerns. The important point is that construction data is both structured and unstructured. It includes numbers, documents, images, models, and sensor data. For AI to use this information effectively, it must move through a pipeline of collection, cleaning, and integration. This slide introduces one of the most important ideas in AI: garbage in, garbage out. AI can only produce reliable insights when the input data is trustworthy, current, and structured enough to be compared across projects. If the project data is inaccurate, incomplete, outdated, or disconnected, the AI output may also be incomplete or misleading. One major problem is fragmentation and data silos. Construction projects involve owners, designers, general contractors, subcontractors, suppliers, and consultants. Each party may use different tools and storage systems. Important information may be spread across PDFs, emails, spreadsheets, local drives, legacy ERP systems, and subcontractor applications. When data stays separated in silos, AI cannot form a complete picture of project health. Another problem is inconsistent standards. For example, one superintendent may record an activity as foundation pour, another may call a similar task concrete slab, and another may simply write concrete. A human may understand that these records are related, but a machine learning system may not recognize the relationship unless the data is standardized. A third issue is incomplete input. Daily reports may be submitted late. Inspection forms may be missing required fields. Schedule updates may not reflect actual field conditions. Poor connectivity on remote or temporary job sites can also interrupt sensor data. These gaps weaken the dataset and reduce confidence in AI-supported analysis. Finally, weak version control and poor data lineage create serious risks. If an AI forecast is based on an outdated schedule update or an old cost estimate, it may create false confidence. Project teams need to know where the data came from, when it was updated, who approved it, and how it was used. The goal is not perfect paperwork. The goal is consistent information that can be searched, compared, validated, and reused. Data governance is the trust layer between construction data and AI-supported decisions. Governance defines how information is created, validated, stored, accessed, protected, shared, and reused across the project lifecycle. Without governance, even a large amount of data may not be useful for AI. The first responsibility is to create and capture data consistently. Field reports, RFIs, cost entries, inspection records, and schedule updates should follow a clear format from the beginning of the project. Required fields should be understood by the project team, and people should know why accurate data entry matters. The second responsibility is to validate and control data quality. Before information enters an analytics or AI process, it should be checked for completeness, accuracy, and consistency. For example, a daily report with no crew size, a schedule activity with missing logic, or a cost record with an inactive cost code should be flagged before it is used for analysis. The third responsibility is to store, access, and secure project information. Project data should be stored where authorized team members can find the current approved information. Access permissions should match project roles. A superintendent, project manager, safety director, subcontractor, owner, and designer may not need the same level of access. The fourth responsibility is to integrate and reuse data. An RFI may affect the schedule, cost forecast, submittal review, field instruction, and closeout record. If these systems are disconnected, the project team may miss important relationships. Integration allows AI to compare information across documents, models, schedules, and cost records. Finally, AI outputs still require human review. AI may identify patterns or generate recommendations, but final decisions must remain with qualified professionals. Audit trails, source references, revision histories, and approval records help managers understand how an AI-supported recommendation was produced. To prepare project data for AI, construction firms should focus on practical, usable steps. The goal is not to collect every possible piece of information or to make all data perfect before starting. The goal is to make important project data accurate, consistent, secure, and useful for a clear business problem. The first best practice is to establish a common data environment, or CDE. A CDE is a secure platform where drawings, BIM models, schedules, RFEs, submittals, field reports, issues, and communications can be stored and managed. A CDE helps create a single source of truth and reduces the risk of version conflicts. The second best practice is to standardize key fields. This includes naming conventions, folder structures, document classifications, cost codes, activity labels, location breakdown structures, and status fields. Practical standardization is more valuable than unnecessary complexity. Firms should begin with the fields that managers actually use for estimating, scheduling, project controls, and communication. The third best practice is to connect systems through API and middleware. AI works better when ERP systems, BIM platforms, scheduling tools, field applications, and analytics engines can communicate with one another. These connections reduce manual re-entry and help AI tools work with current project information. The fourth best practice is to automate data validation. Automated rules can flag missing fields, duplicate records, inactive cost codes, or unusual values before data enters an AI pipeline. This improves reliability and helps project teams identify data problems earlier. Overall, AI readiness is not only an IT issue. Project managers, estimators, schedulers, superintendents, safety managers, cost engineers, BIM coordinators, and executives all influence the quality of construction data. This case study focuses on Autodesk Construction Cloud, or ACC, as an example of how data foundations can support AI in real construction practice. The key lesson is not simply about one software platform. The broader lesson is that AI becomes more valuable when project information is centralized, standardized, permissioned, and connected. For many years, large contractors have struggled with disconnected project information. Design teams may work in BIM software, schedulers may use Primavera P6 or Microsoft Project, field teams may rely on mobile applications, and cost information may be managed in separate ERP platforms. When information is divided across many systems, AI has difficulty forming a complete and reliable view of the project. ACC addresses this issue by functioning as an integrated common data environment. It brings BIM models, 2D drawings, RFIs, submittals, cost information, field reports, and issue tracking into a coordinated platform. This creates a stronger foundation for data-driven decision-making. One important feature is standardization through project templates. Templates can help enforce consistent folder structures, naming conventions, permissions, and workflow rules from the start of a project. This reduces variation from one project team to another. ACC can also support AI tools such as Construction IQ and AutoSpecs. Construction IQ can analyze project information such as subcontractor performance, RFI activity, safety observations, and issue records to help identify predictive risk areas. AutoSpecs uses natural language processing to read specification documents, compare them with historical standards, and identify missing submittal requirements before fieldwork begins. The final takeaway is this: AI is not a tool that can simply be added at the end of a project. It depends on disciplined data management. A common data environment, consistent standards, clear governance, and interoperability are what allow contractors to turn fragmented project records into a practical foundation for prediction, coordination, and operational improvement.